Good afternoon. Yesterday, we discussed a recurrent neural network, the concept, and we also discussed the vanishing gradient and the exploding gradient descent problems. Because of those two problems, then we said improvement for the standard RNN network is we use long short-term memory networks. And we also discussed the general architecture about LSTM networks. And the major difference between LSTM and RNN, the standard RNN is, the standard RNN is a recurrent neural network. So it uses the previous time step, the hidden layers output plus the current states input. So it uses both of them. Okay, so it's a feed both of this as the input for the current state, and then calculate the current state's hidden layers output, and then feed it to the next time step. So that's the general standard recurrent neural network. So it will only take advantage of previous time step. And also for RNN, it's beneficial to sequence data. So it is time-sensitive data. And if we just use what we previously learned, like feed-forward neural network, then it cannot serve well for sequence data. Okay, so that's why we starting discussing the recurrent neural network concept. And we also mentioned the LSTM. So the major difference between LSTM and RNN is LSTM. It's not only use previous time step, the previous single time step is hidden layer output. It also include multiple previous steps. Steps is a contribution to and plus the current state. And it's going to feed for the calculation for the current layers, hidden layers output. So over here, so we have short term and we also have that long term. So that long term is not just the previous, it also multiple may involve multiple previous time steps impact. Okay, and the general architecture is depicted in this diagram. So in this diagram, so the top arrow part input, that's for the long-term memory, and the lower arrow part, this is for the short-term memory part. Okay, and if you recall for LSTM, it involves 3 parts, always has 3 gates. Okay, and so regarding this part, we call it a forget gate. And this part we consider it as input gate. And this part for the output is called output gate. Okay, and then let's just do a quick review what we already learned last class. Okay, and so this top part is the long-term memory from the previous cell. Okay, so we can identify it as like C t minus 1. So here, this is t minus 1 time step. And this is the current one. And it's represented as t time step. And this is the future one. So it's represent t plus 1 time step. Okay, so this C t minus 1 is the cell result, cell state from the previous time step. Okay, and here this input is hidden layers output from the previous time step. Okay, so for this part, so this part is the current input. So X is the input. And the previous layers, hidden layers is output. And both together, we apply sigmoid activation function. Activation. So basic sigmoid activation will give you between 0 to 1, the result. And then we can see, and this result then together will multiply by the previous time steps long-term result. Okay, so if the sigmoid result is 0, then that means you are not going to consider the previous layers cell result. So you will forget it, the long term. Okay, so we will omit the long term impact to our neural network, to our neurons. Okay, so that's regarding this part. Okay, and then so for this part, this is for the current state calculation. So for the current state calculation, similar, okay, we still consider the hidden layers output from the previous time step and the current state's input. And similar as, it's the same thing as the sigmoid calculation for the forget gate. Okay, together, so we have some output here. And at the same time, for the hidden layer and the current input, we also going to do the tangent calculation. And this is, the purpose is to do vectorization of the input. And the vectorization will generate the result between 0, 1 to 1. Okay, so kind of we normalize the result. And then both together, we are going to multiply these two results. Multiply, okay, and similar, if the sigmoid is 0, then that means it will not play a role in the training, is it? But if it is close to 1, that means it's going to play an important role in the training. And then this result will be added. So this part is a previous calculated. So this considering the long-term impact. And this is the current impact. So then we are going to add the long-term impact and the current impact together. And both together, the addition result will be the current cells impact. Okay, so this is a memory cells impact. And at the same time, we also over here is going to be the output gate. So for the output gate, on one hand, we have the long-term impact. So the long-term impact already add. So it's from all of the previous timestamps impact and the current. So it will keep track the historical impact here, okay, and make it as the current timestamps impact. And at the same time, we also calculated the current hidden layers output. Okay, so this result will be what? So it will still take the sigmoid. The sigmoid will be over 2 parts. One is from the previous hidden layers, and one is the current state's input. Okay, so we have this sigmoid result. Okay, and at the same time, we also take the tangent of the result of the current state's calculated long-term impact. Okay, and then we multiply both results, and this is going to be the calculated current state's hidden layers output. Okay, so based on this complete discussion, we can clearly see this LSTM network does consider the long-term impact also. Okay, so that's why we say this is an improvement over the standard RNN. Okay. Okay, so this is the general discussion about the LSTM. Okay, so just like previously we discussed, is it so the top part, the C part represent the long term, and the bottom part, arrow part, the H part represent the short term. So that's why it's a long short term memory. Okay. And then let's see. So for the calculation, like this is the sigmoid. Okay, sigmoid, and this W is the weight. So the weight is for the current state of the previous timestamp or the next one. Okay, so this is regarding weight, and this B represents the bias. So this W and B concept is similar as what we already learned in general neural network. Okay, then let's see. And tangent, we also learned. So whenever you take a sigmoid or tangent, so those are called activation, okay, function. And the weight is also different. Okay, so be careful here. And for the output, okay, output gate, then output gate, it also has its weight and bias, okay. Okay, so over here, it gives a more detailed explanation, just like what I described in the diagram of the LSTM's architecture, okay. Okay, and so we already discussed all of this information, okay. And previously we discussed why we need LSTMs. Okay, so here it explained a little bit of more. Okay, so LSTM that can be used to solve problems faced by regular RNN model. Okay, so it can solve long-term dependency problem. If your problem doesn't involve long-term dependence, then you don't need to use this. You can just use regular RNN, okay, the standard RNN. And also it solves vanishing gradient problem and exploding gradient problems, okay. And also here it explains more as the central part of LSTM network is the cell, and we already saw that. Is it? And the cell state, is it? So we have three different gates, okay? And the cell state also provide certain level of memory, is it? So that the LSTM can remember the past, is it? And we explained, is it? So basically, sigmoid activation function plays also quite important role, is it, on the input, and the input is based on the hidden layer, is it, as well as the current input. And it's not just this, it's also the cell information, cell state, okay. So this is why we need LSTM, okay. And here it just kind of review what we previously discussed. So for forget gate, is it? So the forget gate through the sigmoid. So here is the sigmoid. And this result, if it is 0, then that means it's going to be forget. Is it? If it is 1, then it's going to be keep. Is it? And here similar, okay. And we use sigmoid, also consider. So the input part for forget gate and input gate are the same. Use sigmoid based on the previous hidden layers output and the current input. Okay, but over here, once you find the cell state, is it? The cell state. So the cell state will also contribute to the output gate. Okay, to the output gate. And the output gate will generate the current state, the hidden layers output. So the long-term dependency also contribute to this part. Okay. Okay, and the equations, we already saw that. Okay, and so in this diagram, so here we have CT minus 1. So this is CT, okay. And here you may say, okay, you have the tilde 1. As it, so this we call it a candidate. Okay, candidate. And so here we emphasize more as for RNN and LSTM. They are used for sequential data, okay, in sequence. So sequence is normally with its time dependent data, okay. And so the data is going to be in sequence, in certain order, okay. They are not independent of each other. This is different from what we learned before, okay. The multiple layer perceptron and the CNN, okay. For the general neural network and the concurrent and the convolution neural network, okay, they are not able to handling the order of the input samples. Okay, they cannot take care of the sequence. Okay, and for those one, the input is independent of each other. Okay, independent of each other. So the weights are updated independent of the order. It's not, it doesn't have the order. Okay, it's purely independent of the order. Not like the time dependency, is it? So the input has order, and that order depends on the time. And based on the time, certain input will have certain output. Okay, so this we need to be very careful. Okay, so that's the key part for RNN. And the different category of sequential data, and for RNN we also discussed. Okay, the different types, and an RNN model for sequence, okay. And generally, whenever we mention a RNN recurrent neural network, we can use this diagram to represent. And here we have an arrow back to the hidden layer itself, okay. So this just means that the hidden layer will get its input from the input layer and also the hidden layer. Okay, but from this hidden layer, it's from previous time step. Okay, and in the regular one, feed forward, there is no time step. So no time step involved. Okay, so that's the key difference here. Okay, and over here, it also shows us the single layer RNN. For RNN, we can also have multiple layer. Okay, so for single layer, and if we just draw with the feedback to itself, then we just have a single neuron here. Okay, if we unfold, then we can describe it like in the right diagram part shows. And over here, we also see the different time step, okay. For multi-layer, okay, then we can see, so this is the first hidden layer, this is second hidden layer, okay. And if we unfold it, then we will see for the second hidden layer, it takes the current hidden layer's output plus the previous time steps, the second hidden layer's output. Okay, so we need to be careful here. Okay. Okay, and for the weight matrix, okay, the weight matrix. So we have the weight matrix, is it between the input and the hidden layer, and the hidden layer to output layer, and also the one that is from the previous hidden layer to the current, from previous time step to the current time step. So there are different kinds of weight matrix, okay. So the weight matrix is regarding the input versus the neurons, okay, depends on the number of neurons. Then the number of weights is also going to be different, okay. Okay, and so here gave us a very general expression, okay, about the weights and the activation functions relationship. Okay. Okay, so that's all the concept part for the RNN. Okay, and what next we are going to discuss is about some simple examples. Okay, so the first example we are going to take a look the univariate LSTM model. So how we use it. Over here, we use tensorflow, okay, a high level one API, okay, so Keras. And for RNN, because it involves sequence data, okay, so we also need to do data preparation. So for LSTM model, we already see, is it? So it's going to train the network to learn some function that are going to map a sequence of past observation. Then you can predict the new result based on the sequence of data, okay? So over here it says the sequence observation, it must be transformed into multiple examples, okay, so that the network can learn. So here to give us an example, so we here have univariate sequence. So this is a sequence of data, okay. So we want to predict, suppose, what is going to be next, the next one. Is it based on the pattern, we can kind of guess it's 100 and 110, 120, is it? But the question is, how do we let the machine learning to know the prediction? Is it based on this sequence of input? Okay, so what over here we are going to do is we are going to divide the sequence into multiple input and output patterns, and we call them samples. Okay, and what over here, the time step we are going to take as 3 time step as input. Okay, so every 3 we count it as the 3 time step for the input. Okay, and 1 time step then is used as the output. Okay, so then in this case, 10, 20, 30 is 3 time steps. Okay, and 40, that's the Y, target value. Okay, so X, we have XT minus 1, XT and XT plus, XT minus 2, XT minus 1, XT. Kind of, is it? Then we predict the result, is it? So this is, be careful, okay? So here, the data sequence, if you take a look, compare with what we learned so far, is a little bit different. As a previous, we explicitly have features and target values. Why is it? And here they are all in one sequence of data, is it? Then you find the input value as sample and give the one of it as the target value y. Okay, then so we first take this first three and then this as the target. So we kind of do the windowing, is it? Then the next three and the 50 is going to be the output. And then the next three is it? And then 60 is going to be the y value. Okay, so it's kind of like a window you're sliding, is it? So in this example, they had to provide a function called the split sequence. And then this split sequence, then will generate the X samples, multiple X samples, and the Y results. Okay, so that's what it's going to generate. Okay, so anyway, so this function, the purpose is to have a linear sequential data, then split it into multiple samples. Okay, with 3 time steps. So this is multiple samples. Okay, so this is one sample, second sample, third sample, as a sample. That's what this method is going to do. And then let's see. So we have this raw sequence data, okay? And we define the time step. So we pass into that function and we can see the result. Okay, so this is the result, okay? So totally we have 6 samples. Okay, and then the next one, the first one we are going to take a look is the vanilla LSTM. Okay, so the definition for vanilla LSTM, basically it's a single layer, single hidden layer LSTM units. Okay, so it just have one input and one hidden and one output. Okay, so this is called the vanilla, okay. And over here, it says the key in LSTM is we need to know the shape of the input. Okay, so the shape is as the input for each sample. Okay, each sample in terms of what? In terms of number of time steps and the number of features. So in our previous data, the number of features, we only have 1. Is it? And number of time steps, we have 3. Okay, we have 3. So that's for the previous sequence of data, okay. And like over here it says, we are going to have multiple samples, is it? So the input, it's dimension of the shape. So time of steps, we already know in our case is 3. Features is 1, is it? And how many samples is it? In our case here, it's 6 samples, okay. So we needed to also consider the shape, okay. And Then for the LSTM units in hidden layer, basically is neurons. In this case, we are going to use 50 neurons, okay? And the output, we only have one, okay? And it's going to predict a single numerical value, okay? And also over here, is also said, the model is going to be trained with Adam of the stochastic gradient descent, okay? And optimized, then we use the mean square error for the loss function, okay? So this is a cost function, or sometimes we call it a loss function. Is it for the neural network training, okay? And then what next is the very first step is we need to, because for the LSTM, you need a 3D dimension of data, is it? So the number of samples, okay, time steps, and the features, okay. And once I have that, and then the remaining parts, let's see. So over here, same thing, if you recall in TensorFlow, etc., for neural network generally, etc., we can have a different category, etc. And the sequential is one type of neural network. We also discussed previously, we also have functional, but here we use sequential. So sequential just add layer by layer, okay? So first we define our models and we are going to use a sequential, okay, model. And then we are going to start to do layer by layer adding, etc. So the first we are going to add our hidden layer, etc. So we have 50 neurons defined. And we specify the activation function here. We use rectify linear unit, okay? And the input shape we also defined. Okay, and then the next layer after the hidden layer is going to be output layer. For output, because we only have single output y, etc. So its number is 1. Okay, so this is a model, and then we compile the model, okay, specify with the optimizer and the loss function. And then we can start to train the model with the provided data. You can also specify how many iterations it want to do the training, etc. And if you want to output the intermediate result or not. Okay, so this part is regarding the training part. And then the next part is we do the prediction. Okay, so in this case, we are going to predict because that's the last 3 sequence of data, is it? So we are going to, and of course, you still need to reshape it, okay? And here, in this case, you only have 1 sample. And then you can call the models predict with the provided input, is it? And we can see this is a predicted result, is it? By that sequence, we know it's supposed to go with 100. So here is 101. So it's still pretty close, okay? So that's regarding vanilla LSTM, okay? And what the next one try to show is you can also use, it's called stacked LSTM. So what a stacked LSTM is, a multiple hidden LSTM layers can be stacked on top of one another. Okay, and also be careful, it requires 3-dimensional input, okay, for LSTM network. Okay, and it says by default, it will produce 2-dimensional output. Okay, and but if we do some special arrangement, assign this argument as true, okay, then we can get the 3D required result. So here, similar, still do that split sequence. Okay, here's the input data, time step, and reshape the data. So here the key point is for the sequential data, okay, or sequential model. The sequential model, we first add the first hidden layer, okay? So it's still 50 neurons. And so over here, we are going to take care of the hidden layers output dimension issues, okay? And then we add the second 50 neurons hidden layer, okay? And here is the output layer. And we do the fit model and we do the predict with the result. And you can see, even though we add another hidden layer, the result is not that better than just with a single layer, okay? And there is another type of LSTM we can use, is called bidirectional LSTM. Okay, you can also use. So it says sometimes it may be beneficial to allow LSTM model to learn the input sequence, forwarding and backwards also, and then concatenate the both interpretation. Then in this case, it's called bidirectional. Okay. And for the bidirectional, it says for univariate time series forecasting, then what we do is wrapping the first hidden layer in a wrapper layer called bidirectional, okay? So let's take a look using that example. So all the previous part is pretty similar, okay? Then we start defining our model as sequential. So here we start to adding, is it? When we add in here, we call adding bidirectional, is it? And this LSTM, then it's going to be wrapped within the bidirectional. So then this is going to both forwarding and backwarding, okay? So it's kind of, you only have a single layers of LSTM defined here, okay? And the result, for the prediction result, we can see it's pretty close to the first vanilla one, okay? Okay, so that's this example. And over here, we have another example from our previous TensorFlow discussion, okay? So let's see what that is. Okay, this is also regarding the RNN. So it's pretty similar. It's a sequence of numbers. As a sequence of now, we still do split split sequence. Okay. Okay. So what over here is going to discuss this example is about a car sale data set. Okay, and this is about monthly car sale. Okay, over maybe 2 years or something. Okay, I don't remember exactly. Okay, but anyway, so it's some car sale data. Okay, and as usual, we read the CSV file. Okay, and then we get the retrieve the values, etc. And here, the time step, in this case, we define it as 5, okay? Then we can still call that to split sequence function to generate. So here is to generate the samples. Okay, after which we need to reshape, etc. And after we reshape, and here, we are also going to do train and testing. We're going to split the data into train and testing. And what here we are going to do, we manually do that. Okay, so we define, okay, the first trial is going to be for the train, and all of the remaining is going to be the testing data. So that's how we do that. Okay, and after that, it's the same thing. We do the multiple. So over here, we can see we have, we use the sequential model, okay? The first hidden layer is LSTM cells, okay, LSTM layer. And activation function is defined, and also it defines the kernel initialization, okay? And after that, we basically kind of do fully connected. So this is just, so basically this two has nothing to do with RNN, okay? This is just general neural network layers, okay? So fully connected. Connected, that we also specify the activation function, and the output layer, we still just have a single layer, okay? And then we can compile this model that specify the optimizer, the cost function, and the metrics that we are going to use to measure the performance, okay? And then we can train the model called fit, and also over here, we also do the batch processing. So you can specify the batch size, and you can also do validation, okay? Specify with the validation, and then we do the evaluation with the testing data, okay, with the testing data. And then we can directly collect the performance metrics, okay? So after we do so we train with the training model, that, and at the same time here, you specify the validation data with the testing data, okay? And then what over here is we are going to evaluate the model. That when we evaluate the model, so here we collect the performance metrics. Okay, so we collect the data, okay? And we can also do the prediction with, so this suppose is 5 months. So in sequence, okay, in sequence of the 5 months car sales, okay. And then we predict the 6th month car sale based on the previous 5 months car sale data, that we try to predict the result, okay. So we can clearly see here RNN and the LSTM, that it's used for sequential data. Okay, so be very, very careful. It's sequential data. So like our language, it's definitely sequential data. Okay. Okay, so the result in this case, let's see. So the result is, that's a predicted result, and here it also gives us the performance metrics, okay? And if you want to get in TensorFlow, okay, if you want to get a text description of your model, then you can, if you recall previously, we also discussed, you can use this data summary, okay? Then to give you the description about the model, like over here. Then we can see that layer by layer. So first, this is regarding the LSTM layer. Then we have the dense layer, okay? And this is the last layer. And for each layer, the output shape, it also gave us, okay? And you can also generate a plot for the model, okay? If you want, then in TensorFlow Keras, you just import the plot model method, okay? Then you can go ahead to save the model in an image file. Okay, so that's all the basic information about recurrent neural network and LSTM. Okay, bye.